All right, I'm back. I may have found a way to kind of stitch some of these together and do some very basic and terrible photo or video editing. Just bear with me. I'm doing what I can here. It's all about the math, not about how pretty it looks. So what we have here is a new differential equation. And this is one that you aren't going to know how to do right now. You aren't even going to know how to do it at the end of the unit. The point of this is to show what slope fields can tell us, even for situations that we don't know how to solve. And I have an initial condition, f of 0 equals 2. You can see I started to draw that a minute ago. It didn't go great. So f of 0 equals 2, so I'm at 0, 2. And then the slope field tells me not the points that I need to go through. My initial condition gives me 1 point, and that's kind of all I've got. The slope field tells me which direction to go from there. So as I move downward, I start getting closer to some of these that are less steep down here. And so I'm going to start being a little bit less steep. And as I do that, I start approaching even, I'm getting kind of close to a horizontal. So I don't have to hit the horizontal, but I'm going to kind of match it as I get close. And I can see as I move to the right, I'm going to start going uphill a little bit. I'm not going to hit that segment. I'm going to kind of try to match its slope when I'm close by. And as I move to the left, there's not much to do over there. So in my incredibly skilled surface drawing here, I have a shape. Again, it might be parabolic, just based on what it looks like. I actually will go ahead and tell you it's not really. But all we have is a basic shape. Yours might look a little different from mine. That's okay. This tells me to now approximate f of 1. So again, your approximation might be a little bit different from mine. Your graph might be different from mine. But this is saying when x is 1, on my curve, just a decent approximation for y. Here again, your graph might look a little different from mine, so your approximation might be a little different. But mine looks like it's maybe a little bit less than 1.25. I'm going to go with 1.15 on mine. There is nothing perfect about that. The idea here is just saying, you know, based on my graph, which is reasonably accurate, that's my y value, which is, again, just reasonably accurate. Yours could be a little bit higher, a little bit lower. Okay, find the equation of the line tangent to the graph of f at 0, 2. We've done this over and over and over again since last semester. In order to write the equation of a tangent line, I need to know two things, and I wish you could say this. So I'll ask, and you can just yell it out in your own house. I need to know two things. What are they? That's right, point and slope. So point was given to me. I need to go through 0, 2. And then the slope, we know that that's a derivative. It's f prime at that x coordinate. If the x is 0, I need f prime of 0. And so what we need is a way of finding that slope. Well, that, again, is precisely what the differential equation does for us. So at the point 0, 2, the slope of the tangent line, dy dx, is going to be the x-coordinate minus the y-coordinate, because that's what they told me up top. So my slope is -2. If you look over here at the slope field, I have this red point, which they gave me. And then the little segment that was under there had a slope of -2. This is y. The slope's supposed to be -2. So y minus my known y value equals slope times the quantity x minus my known x value. So I have y minus 2 is -2x. That's the equation of my tangent line. I'll sketch it on my slope field to the best of my ability. That red thing is my tangent line. It has the right slope. And instead of curving like the green guy did, to kind of address the fact that slopes change as we move, The red guy just says, well, if the slope were constant, it would be -2. And so if the slope were constant, it's not really, but if the slope were constant, and I wanted to approximate f of 1, then that's saying I'm going through the point 1, comma, something on that red line. Well, that's just a matter of plugging stuff in. Y minus 2 is -2 times my x-coordinate. Y minus 2 is -2, so y is 0. So my tangent line tells me if the slope were constant, which it isn't really, but if the slope were constant, my y value would be 0. Again, over here, you can see that on the slope field in the spot I'm highlighting. If the slope stayed at -2, then by the time I got to x equals 1, I'd have a y equals 0. So you can see my two approximations are quite different. If I let everything curve a little bit, color code that. So if I follow the green, darn it, this is going great, green curve, we got 1.15. But that required us to draw and kind of estimate, and maybe didn't do a great job. If we follow a line, our estimate is worse. We're farther away from what the curve really should do, but we were able to all get the same answer there. Okay. And then a thing that you saw back in Unit 7, everybody's favorite. You saw one question on one assignment, and I said not to worry about it too much because we talk about it later. Well, here it is, tangent line approximations. What we can see on our graph, except that everything's frozen, there we go. What we can see on our graph is that the actual curve, which I've kind of approximated in green, done a decent job drawing it, the actual curve and then this pink tangent line, like, obviously don't match, right? What I want to know is whether my approximation from the tangent line, this guy, whether that is higher or lower than what the real value is. My green answer still isn't perfect, but it's closer because I let my green solution kind of follow the curve and I let the slopes change as needed. So in this case, my pink approximation was well below what the green curve suggested. 0 is a heck of a lot lower than 1.15. So our tangent line gave us an underestimate. The reason for that is that our actual curve had to be concave up from our point of tangency to the x we were interested in. I could be a little bit fancier with how I'm describing that, but it's basically the concavity. Because what we had was a curve that did this, but we used a tangent line that just did that. My tangent line, just visually, is well below the actual solution curve, the actual f of x, just because the green guy is concave up. It doesn't matter where I drew a tangent line. If I drew it here, that tangent line is also below the solution curve. So anytime my actual solution is concave up, then my tangent line is going to be too low. You can probably predict that if my actual solution had been concave down, then anywhere I drew a tangent line, the tangent line is going to give me a higher estimate than the actual solution curve, the actual graph of the real f. Here again, doesn't matter where I draw that tangent line. Tangent line is always going to be over the real thing because the tangent line assumes the slope stays constant, whereas in reality, the slope changes. And on a concave down graph, the slope of f is getting smaller as we go. So the real curve is staying lower than the tangent line. This is the same Diffie-Q we were looking at a minute ago. And just a type of question, you'll see a fair amount, but really nothing too crazy. Describe all points at which solution curves would be increasing. So we go back to some blue sheet stuff. If my solution curve, meaning not the derivative, but the actual y equals whatever, if y is increasing, think for a moment about what else I know. I hope you said that y prime is positive. So I need y prime, also known as dy dx, to be positive. In this case, dy dx, trying to highlight, not working, there we go. Dy dx is x minus y. So I need x minus y to be positive. And to be perfectly honest, that's a good answer. It describes all points where dy dx is positive. Anytime x minus y is positive, dy dx is positive. Another way to say this, if I just move some of this stuff around, so if I add y to both sides, x is greater than y, or swapping sides, y is less than x. All of those are fine. On my slope field over here, I just want to show what that means. So y is less than x. So if I look at where y is equal to x, you can see that's where all of my horizontal guys are. Here, here, here. Everywhere on y equals x, I'd have a horizontal tangent. And for us to be increasing, this one to me is the easiest to interpret. This says my y has to be less than the x. So I need to be below that line. And if you look everywhere I've just highlighted in yellow, all of those segments have positive slope. Everything that didn't get highlighted has negative slope. So nothing too exciting there. Concavity. Again, think back to blue sheet stuff. Solution curve, meaning y. If y is concave up, then we should know that y prime is increasing and that y double prime is positive. Deciding whether something is positive or negative is easier than determining whether something is increasing or decreasing, so we'll go with this. But that means we need to find the second derivative. I'm going to copy what they gave me, and I need to take the next derivative. So, my Leibniz notation gets a little nasty here, but remember, I'm taking the derivative twice of y, doing it with respect to x both times, and now let's actually do it. So, because we have this kind of variable soup here, I'm taking a derivative with respect to x, but the other side has a combination of x's and y's. This means I need implicit differentiation, which just means I need fixer pieces. When I take the derivative of x, I get 1. But just to be safe, it couldn't hurt to do a fixer piece. I saw an x, and I wanted an x, because I was going with respect to x, and we're good. Minus what I used to call the easy derivative of y would just be 1. But the fixer piece says, well, I saw a y, but I wanted to see an x because of what we're dealing with. There's a Java update available, very exciting. And so I have fixer pieces for both of these. This is implicit differentiation. It's never wrong to do implicit differentiation, but sometimes, as we have seen, you get stuff that doesn't really matter. So 1 times 1, last I checked was 1, minus 1 times dy dx. It's not terribly useful just yet, but we're going to make a substitution similar to what we did for some of the others. This has a dy dx that showed up as a fixer piece. Dy dx, they told me from the very start of this problem, dy dx is the same thing as x minus y. So I'm going to make that replacement. Instead of dy dx, I write x minus y. 1 minus 1x, and then distributing, it's a plus y. So this is my second derivative. There was some implicit differentiation there, but I have my second derivative, which now means We just use blue sheet. I need my second derivative, 1 minus x plus y. I need that to be greater than 0. And again, that's a fine answer. If we rearrange this a little bit, I like to isolate the y, just I'm better at visualizing that way. I can add x to both sides and I can subtract 1. That's fine too. Anything equivalent is fine. But this version at the bottom helps me see what's happening. If I graphed y equals x minus 1, then I would be following these little guys, a nice straight line. And this is telling me everything above that line is going to give me concave up curves. Anywhere I start up here, I'm going to have to curve upward. Ooh, that's terrible. But the way that these slopes work, there's going to have to be some curving upward in order to fit what the slope field is telling me. And lastly, same diff EQ, but going back to something we saw last semester and just putting together what we've seen. So f is a particular solution that happens to go through 1, 1. Here, for a real problem like this, I wouldn't have a slope field to work with, because if I look at the slope field, go to 1, 1, and if I just kind of follow what it looks like, I can see like, it looks like a relative minimum. Hooray. As I often do, you have a visual to help explain what we're doing, but for a real problem, we would be doing this analytically. So the trouble here is that a sign chart just isn't going to work. Because as x changes, right, so if I start at x equals 1, as I move to the right, like sometimes my slopes get steeper, sometimes my slopes like change from negative to 0, or from 0 to positive, or negative to negative, or so a sign chart just isn't going to do it here. So everybody's favorite second derivative test is going to take care of it. So second derivative test, I need to do two things. I'm hoping that y prime is 0. And I'm also interested in whether y double prime is greater than 0 or less than 0. So let's see if that's true. Y prime is the same as dy dx. So at the point x equals 1, y equals 1, y prime, which is dy dx, they told me that's my x coordinate minus my y coordinate. We get 0. Hooray. On our slope field, I see that as this horizontal tangent. We also saw just a minute ago that y double prime was 1 minus x plus y. So y double prime, 1 minus our x coordinate plus our y coordinate. We did that on the previous problem. 1 minus 1 plus 1 is greater than 0. And remember, it's those two things together. Y prime is 0, and y double prime is greater than 0. Together, that tells me that my solution curve at this point is concave up, because y double prime is positive, and it tells me that I'm at the bottom of that concave up curve, because y prime is 0. So f has a relative minimum. That is your second derivative test, which we did last semester. I'm just coming back here because the sign chart just literally doesn't make sense. There's too much happening. And then finally, this is completely optional. It's a 2-question thing. It kind of grades itself for you and gives you hints if you got something wrong. But if you go to that web address, then you can just take a look at a couple multiple choice questions, and then of course the homework should help as well. So this has been super fun. I will do it again for the next part of this lesson, and I'll see you guys soon.